Yeah, let's start. Okay, so today we're going to have our last lecture together. So it has been quite a journey, let's say. And so we are covering today topics that we didn't see a lot during the other lectures, but it's actually one topic that is all about templates. And I will try to make stuff, put the stuff easy and simple so you can get this. And believe me that if you understand what I'm going to try to teach you in this lecture, and if you follow me, you will most likely know more than 80% at least of the programmers I know of C++. So templates is a big thing in C++. Most of the people are scared about templates and generic programming in general. My belief is that it's a matter of the syntax. So the syntax ugly, let's say, and the errors are also ugly. So I think it tends to be difficult to debug or to develop. I don't know. So for me, it's actually quite simple if you know the basics. But I think it's our fault from the C++ community that some stuff for us is obvious, and sometimes we don't like explicitly say that this is blah blah blah, and that also makes stuff hard to understand for others. So I will try to give you the very basics today. We are not going to write a full library on templates of whatever, but the idea is that you should know the bare minimum stuff to work with templates on C++, and don't be scared. So first of all, most of my slides will be heavily inspired in Arthur's CPP contacts. So I think I already recommended one of his talks about smart pointers. So he presents stuff really easily. So I highly recommend you to watch his CPP talks. And then the idea behind generics programming is that you separate somehow the data from the algorithms. So in this case, this is not like really like an algorithm, but it's more like a container. So you have a cup of something, and this case is a tea, and this tea you don't know what is that, but you can actually put coffee, tea, water, whatever you rice. So you can put whatever you want there. And then the cup itself is not coupled to the type of data that it holds, right? So that's basically the idea of generic programming. So to do some sort of generic algorithms like sorting a container without having to explicitly know which type of data you're using. So one example of this we already saw when we work with iterators. So iterators is also part of this generic programming idea, where all the STL algorithms in the library, on the STL library, they work on the iterators and not on the data itself. So if somehow you manage to show how to iterate through your container, then you have access to all the all the algorithms in the STL library. Here are two definitions, let's quickly discuss this. So what is programming? The craft of writing useful, maintainable, sometimes, and extensible, sometimes, source code which can be interpreted, and this is Python, or compiled, that this is C, C++, Rust, wherever, by a computing system to perform a meaningful task, right? That's the definition. And then what is metaprogramming? So metaprogramming is the writing of computer programs that manipulate other programs or themselves as if they were data. So one of the key concepts behind generic programming is metaprogramming, that is basically write programs that write another programs. And this sounds confusing, but it's actually really easy, and we will see how to do this. So what is the meaning of template? So from dictionary, so a template is something that served as a model for others to copy. It could also be interpreted as a preset format for a document or file, or can be something that is used as a pattern for producing other similar things. So those are like three dictionary definitions. And then the C++ definition of template, a short version, is that a template in C++ is a C++ entity, and we saw entities on lecture 1, I guess, that defines one of the following: a family of classes, that is called class template, which may be or not nested classes. So a template class will define a family of classes. It's not 1, 2, or 3, it's a whole family. So it can be infinite amount of classes. Or it can define a family of functions that is called function template, which might be member functions or not, like member functions from a given class, right? So that's all the legal definitions. What is the motivation behind generic functions? Is to, again, to split, to separate the data from the algorithm and work agnostic to the type of data. So actually we have the absolute value function here. We saw how to do this with function overloading on previous lectures. So you can actually, so let's highlight some stuff here. So you can actually use the same name for the function. This is in C++, you can't do this in C. So here is the absolute value, and then it can take different type of data as input argument, but if you pay attention to the algorithm or the computation itself, it's actually the same, right? So this is not, so the good thing about this is that you can use the abs function without paying attention to, so you don't need to define an abs for each type. You can overload its name, but it's stupid in terms of you need to write like how many absolute value functions for your program. So now we have for double and int, but also you should do it for long, and then for int, and then for floating point, and maybe, I know, complex type, maybe char, maybe short. And where does this end? So that's the question, where you should end, like writing the same function with the same implementation but with different type of data. So that's where generic functions will come into place to save you from this pain, and also to keep smashing C. So how they solve this on C, we saw this example when we saw overloading. So they just have like a bunch of functions, like, so this is with even different names. So for long we have labs, for long we have LL absolute, and that's all the C++ 99 standard functions defined. So this is basically a pain because you need to pay attention to which algorithm to pick depending on the data and also to the data. So as usual, there is C++ nowadays, and there is modern, and it can save us from this pain. So we will rewrite the absolute value function, but using a template type. This means that this can operate on any sort of data, because the implementation is actually the same, no matter if this is an integer, floating point, double, long, character, you name it. And this here is basically, you see like these 4 lines. Most of the people will say this is a function, but this is not a function, right? Function templates are not functions. They are templates for making functions. That is different, right? And actually you don't pay for what you don't use. So you create a template, and we will see one example now. And then if you don't call absolute with integer type, then you don't need to create the symbol. So you don't pay for what you don't use. In this case, when you do this sort of thing, you always define this function, even if you're not using it, right? So just keep in mind that function templates are not functions. Templates for making functions. This is quite different, and you don't pay for what you don't use. If nobody calls a given function, then it won't be instantiated by the compiler. So let's see one example. So my favorite tool, let's say, for working with templates is Compiler Explorer. In this case, we will see like a really dumb example. So in this case, we have a template for a function that is called foo, that takes no input arguments and actually does nothing, right? So it's a dummy function, right? But I just want to show you how why we say that you don't pay for what you don't use, right? So let's return 0 here, and then if we comment this out, and if you see the assembly code, it doesn't matter actually if you don't really understand this right now. What I'm showing here is that we only have one symbol on the binary that is called the main, that is actually doing nothing. But if we call a given, if we call this template function with the given type, the compiler at compile time will generate this symbol here. So if you see here, there is a void foo with integer type that does nothing, but it is here, right? And if we call the same template function with another type, then the compiler will generate this other function for us. And again, we are not doing anything particular here, so it's basically 0, but you have the symbol now, and you only pay for what you use. Of course, I am using turning off the optimization. If you optimize this code, it will just remove everything because you're not doing anything meaningful. So whenever you work with Compiler Explorer, keep in mind like the optimizer might confuse you, right? If we go for the normal case, like that's how. So in this case, we actually need to have an integer type, for example. So we have this function foo, and then in this case, what I want to show you is that whenever you do this type of functions declaration, and then double, and then, so I could write the absolute value, but I'm just lazy. In this case, what is happening here is that you're paying for something that you don't use. So you are actually adding these three symbols, foo integer, foo of double, and foo of floating point, to your binary, but you're not using it. So this is your application, you're not using anything, and you're paying for it. So this is something also important about function templates. So you don't pay for what you don't use. So let's go back to the example. And this is the absolute value. And we will see more about the syntax of templates now. So the template functions use the keyword template. And then this, so usually this type here t is, so this, so you need to use t, so it's common actually, but you can use bananas here. So this is a name, so you pick it, and in this case this template function will take as template arguments two types, one is t and the other one is s, and in this case we'll do something, right? And then remember that a function template defines a family of function, right? It's not a function itself. And then this is one example of using template functions. So as usual, my recommendation is you should check it on your computer. And actually, if you use Compiler Explorer, you can actually get an insight of what's going on behind the scenes, right? But this is just an example, so let's go through it. So we have the absolute template function, and then we have two numbers, one double, one integer, and then we will call the absolute value function with type double, right? And then we pass this double argument, and then we get the result. And this auto is basically a double because t is the same input argument as the output. But something that you can also do is to skip the angular brackets and then just pass x. And what is happening here is something magical that is called type deduction. So you have a family of functions called absolute, and then the compiler sees that you are actually trying to instantiate one function from this family of function, and then you're trying to use the type double because x is double, right? So here it's the declaration, and then it can infer the type from your call, and then you don't need to do this angular bracket syntax. So this is something called type deduction, and we will see more in details. Something that is extremely important about templates is that templates lives in a static world. So this is the lecture number 9, that is the 10th lecture that we have together. And I think that I say the word static on all of the lectures. So it's really important that you understand that whatever is involved with templates will happen at compile time. So there's two conclusions about this. The first one is that a lot of people doesn't know how to use templates. or it's confusing or whatsoever. And one of the reasons is you don't reason on a proper way. So whenever you're trying to do something with templates, you should ask yourself the question, do I know this at compile time? No matter what you're doing. So always remember this question. Do we have this information when we build the program? Or is something that will happen at runtime? So for example, if you want to write some sort of algorithm, and this algorithm depends on, I know, sensor data coming from a sensor, of course you cannot do anything with this data at compile time, because it's something that will happen at runtime. When your application is running, it will take the input sensor data and will do something. If you don't have this information at compile time, then there's no way you can do something with templates. And the second conclusion is that our world, the roboticist world, it's quite dynamic. So usually we work with data coming from sensors and whatsoever. So it's actually very unlikely that you, as a roboticist programmer, need to use templates a lot, except when you're writing libraries or like utilities or whatsoever. But for the core algorithms that you might use, most of the stuff, 99%, will happen at runtime. So with this, I want to give you an advice that don't get really excited with templates. So use it wisely. And I will show you some examples on how to use it. So for example, if you need to write the ICP algorithm, then actually there is nothing you can template. So you cannot write a template for this because all the data association and whatsoever would happen at runtime. So there's nothing you can do at compile time. And this means that you should not be thinking in this whatsoever, right? So keep this in mind. So if we go back to this example, so let's comment this out. And then let's call foo with integer. So this is compiling in this moment, and this function got generated at compile time, right? Everything about templates must happen at compile time. So here, this type integer is already defined at compile time. You cannot put here like a variable, like, I don't know, like integer x and put x here, because x first, it's not a type, it's a variable. Now it's failing, of course. And then even if this, for some reason, is like a variable type, so forget about this, but this is not going to happen. This is something that you cannot guarantee at compile time. So right now here at compile time, you need to say, okay, integer, we know who is this guy. Let's create a function for foo with this type of data. Okay, and then we saw two definitions of function templates and template classes. So template classes will create a family of classes. So a template class. So class templates are not classes. They are templates for making classes. So it's different. Sounds funny, but it is what it is. So in this case, wrong key binding. So in this case, so we have a class template or template class that is called my class. Will take as input a template parameter, a type t. Remember, this t is just a letter, could be bananas. And then inside this class, I will have a private data member that is called x, right? And then if you see, all the types are t's, so we can instantiate a class that works with integer, double, wherever, without repeating the code. So the compiler will do the job for us. So all about templates is living in the static world, something that will happen at compile time and will make your compiler suffer. So whatever you do with templates, it's something that is happening at compile time, and this means that the program that is running there is the compiler that is generating another program for you. And that's why this is also meta programming. Because when you create a class template, it's in sort of way, it's a meta class, because the compiler is in charge to generate a class for you at compile time. So you can have it whenever you need at runtime. And then the same holds true for classes and template functions and template classes. that you don't pay for what you don't use. So if you don't call my class with integer type, then the class will not be instantiated, then the compiler will not generate it, then you're free, right? You don't get this. And how you use this? So basically you call my class, and then with Angular brackets, you specify which type you want to be instantiated at compile time, and then you just work as usual with classes. So actually, std vector, for example, is this syntax. So std vector is a class, and then at compile time you need to say, I want this vector to be of type t, and then the compiler will generate a vector for you at compile time. So the C++ doesn't ship with any vector class. Ships, the standard library ships with a template class for creating vectors. If you want to use integer vectors, then the compiler will generate one for you at compile time. I am being very repetitive with this, but it's actually the most important thing about templates, these ideas. And then template parameters. So what is all this stuff that is going on between the Angular brackets? So my feeling is that these Angular brackets somehow scare people. So I know, because they are like ugly, and this is one of the reasons people doesn't want to use templates at all, because the ugly syntax, right? For me, it's just syntax, so you shouldn't worry a lot about this. So every template, this could be a class or a function, is parameterized by one of more template parameters. And then the syntax is basically, you have the template here, the keyword, this is from the language itself, and then here you have a parameter list, and then you have the declaration. This could be the class, the function, wherever. And what is important here is that from now on you can think, so let's pick the function template as example. You can think that you have like two parts, so two ways of passing arguments to the function. One way of passing these arguments is passing arguments at compile time. I see that the video is lagging. So if you can hear my voice, please let me know in the comments, because my feedback completely lagged. I think we need to go for the backup one. It's working. Okay, so it's on my end. Okay, sorry guys, it's connection mess. Okay, so what I was saying, okay, thank you guys. So what I was saying is that now whenever you see a template function, you have two ways of passing arguments. One will be to pass arguments at compile time, and this is something static, and the other one is passing arguments at runtime, and this is dynamic, right? So let's pick two colors. So red will be whatever you need to pass to the template function at compile time, and this is the template parameter list. And then at runtime, let's pick green, will be this value, right? So you can think whatever you pass into Angular brackets, so it's the same as passing arguments to a function, but in this case you're passing arguments, template arguments, to a template function. It's all confusing, but it's actually, for me, it's easy to think like you have two ways of passing stuff to the function, one at compile time, the other one at runtime. Again, it's very unlikely that you can pass something meaningful to an algorithm that needs to work with data at runtime. It's very unlikely that you can pass this data at runtime. So it's something that it's very unlikely that you will use a lot. So in this case, we have this template for a function that is accumulate vector, and then we will take one t. I guess that this t is basically a type of it's a type of the data we want to use. And then in this case we have this other guy, that is this other template parameter that is a size t. So in this case, it's not a type name. So this is basically, this is an integer type. This is a real thing. So you know who is this? It's like, could be 0, 50,000, whatever. And then we will call this n, and actually the same way you can do for default arguments for functions, like that this happened at runtime. You can say, if no one specify you this value at compile time, then just pick 10. And what is this function, template function, going to do? It's going to create a std vector of the type t, and then the value will be repeated n times, right? And then you just return the sum of all the values. So think the template parameters the same way as function arguments, but at compile time. And here is an example. So again, you should try this at your own place. It's better if you do it with Compiler Explorer also, so you know what's going on behind the scenes. So we have this accumulate vector. Whenever we call this, so we are saying, okay, we are not passing any template arguments here. So if you see there is nothing here, if nothing is between the angular brackets, then no template arguments are being passed to the template function. And then what is going on here is that the compiler is doing all the job for you. First, you're using 1, so this is an integer type. So the compiler can go ahead and say, okay, this t is an integer, so I will deduct a top for you. No need to tell me. And then because you have a default value for this template parameter, the compiler say, okay, I will pick n10, right? Then you will create a vector with 10 values equal to 1, and then when you return, when you do the reduction, you will get a number 10. So you should try it at your computer and see that this is actually 10. So this is one example of calling this template function. The compiler will instantiate an integer type with n equals to 10. So the other usage is, so again, now if you see, so here, so this is the function, and then you have two ways of passing parameters. One is at compile time, that actually we pick red, I think, when we do the example. And then the other one will be at runtime, right? So this accumulate vector function, now you're saying the type is floating point. Why? For example, because this 2 is actually an integer type, but you want to cast it to floating point for some reason. So at compile time, you say, okay, this type name t is a floating point. So this will generate a function that will return a floating point here, will take a floating point here, will create a vector of floating point here. And because you didn't specify the n template argument, it will use 10 by default. And then it will do its magic. And at runtime, so when you call this function, it will pass this number 2, right? So first it will generate this function, and then when you call this function at runtime, it will pass this argument 2, and then it will run this algorithm, let's say. And then the last way of using this is, again, if you split here, just book, you have whatever comes to this side is at compile time, and this is at runtime. So you say, give me a floating point for the type name, and then use 5. Instead of n equals to 10, I want a vector of 5 elements. And these 5 must be defined at compile time. So you cannot use here a variable. You cannot do int integer size equals to this plus this and then put it there, because whatever comes to the left between the angular brackets must be defined at compile time. So this is again extremely important. This argument, the function argument, once you have the function generated by the compiler, will be whatever you want. Now we have a 2.0, so we know this at compile time, but it could be any variable, because this is a function and can work like this, like any other function. At runtime, you just say, okay, give me accumulate this value, and then you pick whatever you want to send. But remember, whatever is between angular brackets must be defined at compile time. I will repeat it until you get sick. Okay, so type deduction in a nutshell. So the stuff we saw so far is the most important stuff. So what is really what are templates for? When this stuff happens for real. So type deduction. So this is a really nice example. You can try it at your place. So this is basically to replace compiler explorer. You will create a function called foo, and then this puts pretty function wherever. So this ugly thing, this is a macro, a C macro, that is defined on the C standard library, but it do its job for this example. So type deduction for function templates basically is the stuff that the compiler will do for you at compile time. So in this case we have foo, and then if we call this function, it will basically print to the standard output boy foo with t equals to int, right? That's basically what's going to happen. And why? Because this 4 is an integer value, and then at compile time the compiler will inspect this call and say, okay, this is an integer value, and then let me check your class, your function template. You have 1t, okay, it's easy. So you're asking this to be an integer, so I will do it for you. Don't worry, no need to use angular brackets. I will deduce the type for you. In this case, we have a double, and then you might think it's a floating point, but this literal here is a double, so we generate the double function, and if you call this function, you will print this to the standard output. And the same for this string that is basically a const char pointer, right? So this is basically type deduction. It's when the compiler do the deduction for you. Again, try this example, use different values, different types to see how this works. So the rules are here, we just keep it, it's boring. And then here's another example. So let's go through it like if we were the compiler. So first we have a template function. So this is not a function, it's a template to creating functions that takes as template parameters two types, t and u. So let's pick different colors. So this is u, and then here we have a new, here the t. So this is a function, it does something, it doesn't matter, right? And then we have another function that actually takes one template parameter, that is t, and then it takes two input arguments from the same type, t, that we don't know, right? Good. And then let's call f in our application with two integers. So this will go here, we'll check, you'll say, okay, this t is an integer, and then the 2 it's also an integer. So I will create a function for you at compile time with t equals to int and u equals to int, right? Great. And then you call, for some reason, the same template function, but here you say you use the u literal. So this means like you assign it int. It's probably, if you try it at your place, it's probably easier if you create the variables with the type you want to try it, because it's more readable, but here we don't have space. And then the compiler will generate a function at compile time with t equals to int, because the 1 is an integer type, and then with the type u, that is another type, and it's defined at compile time with deduct, that this is an unsigned int. So it will create this second function for you. And then the g function, it takes the same type, so it's two parameters at runtime, but the type name is the same. So whenever you call with integer, this will work. It will generate this g function with t equals to int, so it's only one template parameter. But then if you want to do this, it will fail. And when I say this will fail, I hope you know that this will fail at compile time. So this will not be able to compile. Why? Because you're saying generate the function g, and then the type name, the first one should be, sorry, she is here. The first type name will be t, so I'm contributing to this type deduction with integer, good. And then the second parameter is unsigned int, but then t should be unsigned int. So if the compiler cannot decide if this is integer or unsigned int, it will just abort. So it's not something you can actually do. It will fail. This is the error message. So you know, matching function, whatever. One way of solving this is to specifying with angular brackets integer type, for example. But what's going to happen is that you will, if you do this, you will cast this unsigned int to integer type. But this is basically how type deduction works. So it's not magic. The compiler is smart, it's smarter than I am at least, but it cannot do magic or stuff that doesn't make sense at all. So that's basically the key concepts behind type deduction. And then lastly, you can also do type deduction since C++17, so keep this in mind. So if you work with another standard, this will not work. So let's go through the example. So we have a class foo, struct is the same. Actually, this public is not needed. And then we will hold a data member of type T, and then the constructor will basically take another T, and then we'll initialize this T. And something, so the classic syntax will be this one. So in this case, yeah, so just forget about this. So you will create an object. So let's delete this. So this is not here. Boom. Boom, it's gone. So you will create an object of from the class template foo, and then you say, okay, this T is integer. But since C++17, you can use type deduction and avoid this angular bracket syntax and say, okay, I will pass an integer to the constructor, and actually if you inspect the constructor, you have T here. So this is, I mean, it makes sense for the compiler. It also makes sense when you read it. So you can deduct the type at compile time and then create a class foo with type name equals to integer at compile time. So you can actually do this. And the same holds true for the vector. So you have been using vector for a while, and then you usually do this. So you create a vector and then you use 2 elements, for example, but these 2 elements in this case are integer types. So you can actually avoid this angular bracket syntax. So this, you can avoid it here because you can deduct the type from these 2 elements. Of course, if you pass here an integer type and an unsigned int, you're using 2 different types. At compile time, you cannot guarantee who is T, so this will fail. Of course, just don't use this. I mean, it's easier to read, but it's not common. And actually, if you do this, you will only be able to compile this code with C++17, and then it's going to probably fire back at some point. So that's just an example of how type deduction works with classes. And actually, so this is something that I will like to do live, like how this works and whatsoever. But I will just keep it, and then ideally just try to think about this puzzle on your place, and then we can discuss it on the Discord channel. So you can say, no, for me this doesn't compile, whatever. Of course, you can try to compile it and inspect the results, but try to, before you actually compile it or throw it to Compiler Explorer, just try to think this example on your mind and try to compile it locally on your brain. And then we can like brainstorm on the Discord channel. I mean, if we were on the classroom, I would probably give you 5 minutes to think about this. But here it's going to be a mess using the chat and whatsoever. So homework, do this. And then the last step for knowing all you need to know about templates in C++ for roboticists is template specialization, right? So this is basically mostly the last big topic for templates. So let's say that you have a template for a function that is called isVoid. So again, let's highlight. So this function, sorry, this template for a function will create a family of functions, right? And then ideally, so actually, if you try to read this on a high level understanding, you will say it's a template function that will take any type T and will always return false. No matter how you call this, I will assume that all the types are not void types. So I will just return false, right? But what happened with the actual void types? So what happened if we call this isVoid function with void type in the template argument list? So we actually want a true value. And then for this, we need to do something that is a full specialization, that is from this family of function, you will pick one function, like one particular implementation, and then you will provide the full specialization for this particular function among all the functions in the family. And how you do this with this ugly syntax that is basically template and then angular brackets empty. So if you ever saw this on a program and you got confused, now you know that is basically a full specialization for a template function. And then here on isVoid, so actually there are many ways of doing many syntax to achieve this result. This is the one I use the most. So you will say the isVoid is basically this template function, but with type void. So you're saying you have all these family of functions. It can be whatever, but for void, I am in charge of this. I will provide full specialization for this particular function. And then you will return true, right? That's basically what you want. And then no matter, so again, try this example at your place, no matter how many functions you create with isVoid, you can do isVoid with std vector, with arrays, with floating points, double, you name it, it will always return false unless you use void. Because so whenever you call this template for a function with any type, it will instantiate a new function with the given type and it will always be false, the result, except for void, because it's a full specialization for this particular type. So this is something that is important. For example, if you're working with serialization libraries or with ROS, so if you need to pass a message from one node to another one in ROS, and then the serialization is not implemented, then you will need to provide a full specialization for the serialization for this particular type. And if you are interested in this, I can show you some examples like offline. But that's basically when you will want to use this. And then the syntax is the prefix with definition template, angular brackets empty, and then you gotta write the function definition. And this is like a function. And this, what you're seeing here, is a full specialization for a class function, for a template function, but it's a function indeed. So whenever you do this, you will generate this symbol at compile time. So this is something that will happen. So this is equivalent to write the function. And then usually means you don't need to write any more angular brackets at all whenever you do this full specialization, unless the type can be deducted, like the previous case or this particular case. So we have, for example, size of t, and then this size of is a C function that it's not defined for void. So if you want to define size of for all the types in a C++ program, then we need to do a full specialization for void. And why we use angular brackets here? Because size of does not take any input argument. So whenever we call this function, so if you call size of whatever, you are not passing any argument to the function, so the compiler at compile time cannot deduce this type. So no input arguments, impossible to deduce the type at compile time. So you actually need to specify this. Or the other thing that could happen is that unless t is default. So what you're going to do, for example, in this case, you say, okay, this type name t, again, this is a template argument list. All the rules for arguments holds true. The same is like you can use default arguments, and you say this t will be void unless you specify something different. So when you instantiate this full specialization for my size of, now you don't need to do angular brackets anymore, because the type is void unless you specify something different, right? So that's basically full specialization of function templates. And then actually there's something also that is not super useful, that is called partial specialization. That is basically any sort of, it's the same type of specialization, but itself is a template. So this means that it still requires further customization by the user before it can be used. So for example, you can create this variable. So this is a template variable that is called isArray, and then you say it's always false, right? For any type t, it's false. And then now you will think, okay, but if I want this to be true for like arrays, then I need to do the same as we did like before with function overloading. I need to define do full specialization for array of integer, array of double, and blah blah blah. Or I can say, okay, I will do a partial specialization for any type t, p, that is an array type. So this is a syntax for, so this is a template for an array. So this could be any sort of array, and then the isArray template variable will be true for this type of data. But this is not a full specialization because it's still a template and it still needs to be instantiated at compile time and need further customization. When this happens, when you call this with integer array, for example, then it will go here and say, okay, I will generate this variable for this integer array type, and this will be equal to true. If you do this with floating point array, then you will generate another template variable, and then it will be always equal to true, right? So it's probably confusing, but it's basically it. And then lastly, so this is like a build thing. This is something that people already struggle with Homeboard 3 or 4, I don't remember. So concrete templates are instantiated at compile time. Now you know it. Whatever happens with template will happen when at compile time. And then the linker has no idea about the implementation. And then there are three options basically to work with templates and to split the header and the source. And probably, I think we have time, I will do the example. So let's actually do the example. For this, we need an editor. And then so for now, let's say that let's start simple, right? So let's create a template for a function, template, and then type name, it's going to be t, and then let's call this function void foo. Should be foo or something more meaningful. Let's do foo for now, that's fine. And then this foo will take an input argument, a const reference to a t, and then return x. Basically nothing. Right, so let's actually, no, let's keep this so we can print to that. Let's instantiate at compile time with integer type, for example, and then 5, right? This will basically return 5. And because 5 is an integer, the compiler can deduct the type. So let's first make, and then make, boom, it's working. So 5. And then the compiler can do this for us, so no need to do it. And then make and make. It's still 5. So if I do 5.5, then it will be another function at compile time, and it is working, right? So far so good. So let's say that, so this is a small example. Let's pretend we need to use a real build system, then we need to use header resources, whatever. So let's create a new file called foo.h app, and then let's pragma once, and actually something that, and then let's, it is probably too big. Do this, yes sir. So this is foo.hpp, and then let's move this over here, and then now we include foo.hpp, right? Again, if we want to build this, it's working. Main, it's working. What is happening here is that you have the template for this function here on the header, and then at compile time you include this, and then you know that including a file is basically copy pasting the content here, and then you put it here, and then when you call this, the compiler will be able to generate. But what usually happens is that you will feel the temptation of doing the same that you do for normal functions, that is to do the following. So let's create a foo.cpp, and then can I do this even, come on, stupid VS Code. Okay, this will do the job, I guess. So what you're going to do is you'll say, okay, include foo. This is super confusing actually, and it's really a really common mistake. So you say, okay, oops, change. So you have the header file and you say, okay, I have this declaration and then the definition is here. And then forget about the errors for now. And then why you want to do this? Because you like this idea of like splitting function and whatsoever. But what is happening here is that let's add this actually to the build. So let's add foo.cpp to the build. And then if you already struggle with templates, you will know that this will not work. So let's remove this, it's not needed. Move this here, and then that's a lot of information. So the main application, then the header file with the template class declaration, and here is the implementation. So you will expect this to work, but what will happen is that it will fail at link time. And then you will see the error now. And then if you ever saw this error, I will explain you why is this. So LD is basically the linker, and it says undefined symbol for this foo with integer type, right? And why is this? Because the compiler, when you include this, it will see the declaration. So it will not fail to compile, but then remember that this will be a promise, and then at link time you need to provide a symbol. And you say, what? But I am actually compiling foo.cpp, right? What is happening here? What is happening is that this is not a function implementation. So again, this is a template for a function. So whenever the compiler comes to compile this thing, no one is actually calling foo. So it doesn't see this. So the foo.cpp doesn't see this call. So the compiler will just ignore this template function and skip it, right? And that's why this symbol is not being defined. So you have multiple options here. So the first one is to do it everything on the header file. And then for this, it's, so if you're writing like libraries, like Boost libraries are all like this, you just put everything there. And remember that in this case, and this is really important as well, you're actually not putting the implementation on the header file. You just have a template for a function there, and then when you include this file and you call a function, the compiler will generate the function for you. So this is different. It's not like putting an implementation, like a normal function implementation on the header file. So that's number one. And then what could happen is that you say, Nacho, I have a lot of function, and I actually like this idea of just showing the API of the function without the implementation because it's readable. It's more readable for me. You can do this, and for that you have two options. The first one that is common but I don't like is that you put this here, and then at the end, at the very end of the header file, you can include another header file that is going to be called foo, and then impl whatever. Some people do IPP, but this is ugly. And then HPP, and inside this header file you put the implementation. So basically what you want to do is to foo impl HPP, and then now if you see this file, so this you don't need, and then here you put the implementation for the class template, the function template. This is really common, and actually when you see this, the foo is going actually to be foo.h. So this is really common if you see on libraries, Boost library, they do this, on PCL library, whatsoever. And then what is happening here, this is like a mess, that when you include this header file, you will see this, and then at the end of the header file, you will include this another header file. And then you know that whenever you include any file, you basically copy paste this into the header file. So it's basically the same as before. So if we try to build this, it should work, and it's not working, of course. Why it's not working? Pragma once, this is a header, so you need to be careful with this. Why? file not found. Okay, why file not found? Full input. Why it doesn't find the file? It's weird. Okay, I will make this work. Why is this not working? So full. So this should be working, and we will make it work. It's the same. Probably I will make this less big because it's hard to me to see, and then come on, this should work. Okay, redefinition of foo. Why is this? Foo? Because I forgot to remove this from the build. So let's forget for this foo CPP right now, and then yeah, now this should work. Come on, trust me, I'm an engineer. And then make. Now it's working. If we call the function, we will see the same. And then what you have right now is basically this split between the header file and the source file. And actually this is readable as well. So you can actually here like put comments, like blah, blah, blah. And then you hide implementation on another file. This actually works and is the same as putting the implementation here. It's a bit funky to see and include statement at the end of another file, but it's basically to make the code more readable. There's nothing but with this. That's one option if you want to split. And then the other option is, let's go back to this, and now go back to main. Let's remove this impl thing, and then you go away, and it's the following. So here on the foo.cpp, whenever you build a model, you need to say right now, okay, please compiler instantiate the function, the foo function from the family for this given type. So let's say that you know that for now you only need to work with integer and doubles. So what you're going to do is you're going to do template, and then you will do double, and then foo. And to make it clear, let's do double here, and then const double x, and then that's basically it. So with this, you're basically saying, it's like calling the function with double type, right? You're basically saying, please generate this function for me. It's the same as doing this, but you're not specifying any argument. This is telling the compiler, please do it for integer, and then for double, sorry. Let's make this, and then here will be int, and here will be int as well. So now, let's try to build this. Now we are building this foo.cpp model, like if we are doing like a library thing, and then now it's not working, of course. Undefined foo int. Why is this? Maybe this is not needed. Okay, so the syntax is different. You don't need to do this full specialization thing. You just say this is a template for this function template. Here, of course, you need the implementation, and now when you make it and build it, it's working. And again, this is actually confusing, but it's simple. My recommendation is try to do the three ways of working with templates. So everything on the header file, two header files, or one header file and one CPP with particular implementations. So in this case, now you achieve this goal of splitting stuff. And I want to show you that this is not actually uncommon on real examples. So if you go to Open3D, for example, this was on geometry, KD3 flan. So there is a KD3 implementation that needs to work with templates. And for example, you have this search template for a function. And then you don't, so here you don't have the implementation for this function. Why? Because you want to keep this easy, so the header file, you want to only have declarations and not definitions. But when you work with templates, you need to provide at compile time the implementation. So if you go to the KD tree, so the .cpp, and if you see ppp, so now here you have this search function. So actually let's do search knn, and then if you remember, this was a template for a function, and now you have the implementation for a t. But remember that you need to tell the compiler which one will be the types that you will be using, because the compiler needs to generate a symbol. This is the third example we saw today. And then it's the same, so template, blah, blah, blah. And then here you do for eigenvector of 3D and for an eigenvector of XD, and that's basically it. So you are only generating two functions at compile time for this template function. So from among all the family functions, you are picking two, and then you are not doing any full specialization. So you're not doing this. You're just telling the compiler, just go and search for the function template, but use type t equals to blah blah blah, and then you will get this. Why you want to do this? Because you want to split the implementation from the declaration between header and source file. And actually, if you say this is stupid, and it's not, because the implementation is the same, and it's much easier to just copy paste this 3-line syntax than copy pasting the full implementation for two types, and then if you change one in the other one, you will forget to change it on the other one, and that's whatsoever. So that's basically it. Here are the three ways of doing it. Again, my recommendation, try it at your place. And then lastly, super easy, const expert basically means try to do this at compile time. So we have been discussing how to do stuff at compile time. In this case, if you try this on compile expert, you will see that this, whenever you return this factorial to 10, this is guaranteed to be computed at compile time. So this function is a function not for the program, but for the compiler. So you're saying the compiler, please compute this function at compile time. And then again, you need to think about like what is happening at compile time and runtime. So this const expert can be also applied for variables. And then if you say, okay, give me at compile times the size of this vector, on this case will not work because the size of the vector is dynamic, and this means that it might change. But this doesn't hold true for an array, because an array you're passing, and now you know what is the meaning of this. You're passing, okay, I want an array of 10 elements, and then the size, it's guaranteed to be 10 at compile time. So this can be a const expression, but this cannot be a const expression. Why? Because this is, you don't know the size. So that's a small detail. So one question is, can you use templates for other types as well, or must all types be defined in the CPP file? So that's a really good question. So if you go for option number 3, you need to define all the types you want to use in that file. So if we go to the Open3D example, you're only allowed to, actually sometimes it doesn't make sense to use it with other types, but you're only allowed to do it with eigenvector of 3D or with eigenvector of xt. If you call this function with any other type, this means it will not work. And this is a really good question, and this will happen. So that's basically the thing. I see lags on my feedback. Okay, so again, these slides were heavily inspired by this CPP talk. It's actually 2 parts, it's 1 hour each. If you have time, just go through it. You will find similarities between the examples there and the one from this slide. It's highly recommended to watch this CPP-Con. So please, if you have time, just do it. And then here are the references. Basically, it's all about, we saw all about templates in C++. I am sure that if you understand this 1 hour lecture, then that's all you need to know to work with templates. Then there's much more information, detail, like variadic templates and concept expert everywhere. It's a mess, but you need to know the basics. You need to have the ability to reason at compile time versus runtime and whatsoever. That's one of the most important things. And then we saw on a live example how to work with the three cases of working with header only files, to header or header plus CPP file for templates, because this is something that is really common to be confused, and it's something that I'm guessing that you're already struggling with. And then that's it. We are going to now I'm going to go through a really 5 minutes course wrap up, and then that was basically the end of the lectures. So we started this journey 10 weeks ago, saying that talk is cheap, show me the code. So I hope I show you as much C++ code as I could. I also promise you that you will get your hands dirty. So there are 9 homeworks. I guess that most of you at least did this, so you know what is the philosophy, and probably after. So people still struggling with build system after 7 homeworks, and that's the idea, that you should get your hands dirty to get through all these issues. We saw how to work with GNU Linux systems. We saw how to work with simple bash programs, how to redirect the standard output, the standard error, and what is the standard input, how a program works in a Unix-like environment. We also saw a lot of stuff from the software development ecosystem. So we saw text editor, linters, test, the static code analysis like clan TDI format. This is clan format, the CI/CD, Git, build system. So we saw most of the stuff for doing real development. So we have one lecture on build system that for me is extremely important, because sometimes you lose the ideas that you want to express in your course because of the build. So the same with templates holds true for the third example. It's hard to make it build, but the ideas are good. So sometimes if you don't know how to build, you lose the idea. We saw how to use CMake to simplify all of our builds. Also the legals, how to declare a variable, how to create functions for C++. I hope I convince you like which one are good C++ practices. There is no book for this. So there's the CPP core guidelines, but they are like really hard to follow sometimes. And I hope that I try to convince you that why it's important to use C++ and not C and whatsoever. We saw how to use containers on C++. They are much better than just using plain arrays. Also, we discussed the difference between the static and the dynamic world. We saw who is using containers in our community. My video is completely lagging. I hope you're seeing this. And also we saw iterators, how to decouple the algorithm implementation from the data. This is basically using iterators. So this is also a type of generics programming. We saw like 15 or 20 STL algorithms, also the C++ utilities like move semantics and other stuff. We quickly discussed the file system library. We introduced how to create new types for C++, and we say why this is super important. We managed to represent an abstraction of the real world with a C++ program. We discussed all the anatomy of a C++ class. We briefly discussed about move semantics. We also saw some object-oriented design patterns, like how to do inheritance in C++, how to do polymorphism, where objects will behave differently. And we also did this at runtime, but also we did it at compile time with the CRTP pattern. We saw other patterns for object-oriented design. And then lastly, we work with memory RAM. I hope I convinced you that there is a huge difference between the heap and the stack and when you should use which one. And then we saw all the memory issues that will come into place if you manage yourself your memory, and then you say, okay, smart pointers will do it for you. It's much better, just use it. And then lastly, this is basically all the summary of all the stuff we saw, and then where to go from now. So we end up with the lectures. So we enter phase number 4, the fourth part of this course, that is the final project. For this, I will not say much words because all the details will be communicated to you in an email, and basically you have from now on, you have like more or less 1.5 months to do this project. And my recommendation is so keep on schedule with the homework so you can start working on the project as soon as possible. And then that's basically it. Thank you very, very much for all your patience across all these 10 weeks. I hope I really gave you some C++ understanding, and from now on, it's all up to you. So I hope you have the basics from my side. I did as much effort as I could, and I hope you enjoy the course as well. So thank you very much for staying with me. As usual, questions, complaints, whatever, you can ping me on Discord. So thank you very much, guys, for staying. Okay, and see you on Friday.